Okay, good morning, everybody. I hope everyone's having a wonderful day. So just a couple quick reminders. So I will be putting out assignment 2 later today. And one other detail you need to know about is that Monday is Victoria Day, so we won't have class on Monday. Our next class will be on Tuesday next week. And also I'll have my scheduled hours for Monday. I'll have those instead on Tuesday. That way I'm still available early in the week. But of course, you're always happy to send me a message. I'm pretty happy, like over email or on your courses. I'm pretty happy to take a look at it. Okay, so last day we were talking about stacks and queues and how we can implement them. In particular, we're focusing in on queues. Recall that in a queue, it's modeling the process of having a line where, say, for example, objects are waiting in that line to be queued in and queued out, or enqueued and dequeued. So what the people will do is they wait in the line, and as soon as they're serviced, they can leave the line or get dequeued from the line. So that is what a queue is. So I wanted to recap just one kind of final summary on this topic, is namely the kind complexities for our stacks and queues. So we talked actually about a number of different implementations for stacks and queues. For example, for stacks, we talked about the array-based stack and our linked list-based stack. For queues, we talked about a linked queue. I also mentioned, just if you're curious about it, there's also the circular linked queue. There's also an array-based queue, but in particular, I talked about at the end of last class about how I could try to adopt the idea from the array-based stack, but we've seen that there's actually an issue with it, so I brought up this idea of the circular array queue as a way to remedy that. So if you're thinking about these implementations, in particular the circular array queue and the linked queue, and the circular linked queue, all of these have wonderful time complexities with a couple of wrinkles. So I wanted to highlight this. So first, when you think about the linked list-based implementation, if I consider all of the linked list-based versions of all of these stacks and queues, all of them take big O of 1, so they take constant time in the worst case. The reason why is, remember, if you think of like enqueue or push, remember all it does is it creates a new node and puts it into the appropriate spot, right? But the thing is we have direct access to where the insertion needs to happen. So to perform that operation takes constant time, and anything else is just manipulating or incrementing counters, for example. So all of those I can do in constant time. Our dequeue or pop operation, those can be done also in constant time because, again, it's just a deletion of a node and returning the result if there is in fact a node in the linked list, right? And all of these, because I have direct access to where the deletion or removal has to occur, I have access to perform these in constant time. So these you can do quite efficiently using a linked list-based implementation. So if you're using a linked list, you can get big O of 1 for every one of the single operations, because you can think of like peek or front. Again, same idea. You have direct access to where the element would be. Size, well, you have a counter, right? You just return whatever the result, whatever the number is empty. Well, you just check if you have any elements or not, right? All of the operations for your stacks and queues, if you use a linked-based implementation, they take constant time, all of them. And the amount of space you use is big O of lowercase n. So remember, lowercase n is the number of elements in the stack or queue. So if you think about this, this is a wonderful way of implementing a stack or a queue. The drawback of it is that, well, you have to create nodes for all of these, and you have to dynamically manage them. But if you know how to implement a linked list, that's not a very difficult thing to implement either. But as a contrast, we also had our array-based implementations, and I made this caveat, I made this note about the capacity or length of the array. Do you remember last day I said, I'm going to assume that the capacity or length of the array that I'm going to perform my insertions and removals on is always going to be big enough. The main reason why is because when the array becomes full, meaning if I try to do an insertion when there is no more room, I have to resize the array. So if I assume that n, my number of elements, is less than or equal to capital N, the capacity, then it takes big O of 1 time. It's not very hard to see this is the case. I don't like using that phrase, but most certainly one way you could just see it is, okay, I know exactly where the insertion has to happen, right? And also I know the same thing when I want to refer to a removal, right? And if you're not convinced by this, I encourage you to take a look at those algorithms again. You'll see it's all it is direct manipulations. There is no like, oh, I have to scan through the array or anything like that. It's just direct manipulation, modify a counter variable. So note that it may not be true if the array becomes full. So the one thing I need to stress is that more generally, you cannot make this assumption. So this is something that you would typically want to do in practice. So you want to ensure that your array maybe is big enough before you set this whole thing up. But I have some good news for you. So first I'll start with the bad news. The bad news is that more generally, if you're using an array-based version of a stack or a circular array queue, both of these take big O of lowercase n, remember that's the number of elements, time. So note that that isn't constant time. Can anybody remind me why it's big O of n as opposed to big O of 1? Can somebody think of the circumstance why it might be the case that it doesn't actually take constant time anymore? So I've given you the setup before, but I want you to just remind me what exactly we're missing here. So what's the scenario that causes it to take linear time as opposed to constant time? So think of the configuration of the data structure at that time. If I attempt to do, say, for example, a push operation or an NQ operation. Yes, exactly. So one thing I do want to, exactly. So it's when the array becomes full, if I do a push or an NQ operation and the array is already full, I'm going to have to copy them over into a new array that is longer. But the thing is that we might need to make the array much bigger. Now, I'm going to give you a little tip in a moment about how you would resize the array. But one remark I do actually want to make is that if you're using an array-based implementation, if you don't really care about decreasing the length of your array, one thing I want to note is that if you just want to do like where you just do the removals, one thing you can get away with is that for the array-based ones, if you do a DQ, like if you're doing DQ or pop, you can still get the big O of 1, just this is under the presumption you don't do any resizing for the array. It's sort of the issue, like the primary issue is when the array becomes full, right? I just wanted to mention that. But some people, what they'll do for the sake of optimization, what they will do is that if the array becomes too long or you're using too much space, some will have it where if you only have so many elements in your array, what you do is you would actually perform something that's pretty much the opposite of making it, say, twice as long. You make it half as long, for example. So if you don't want to use as much space, you'll just reallocate it to a new array that's shorter, and you would just copy them over again. So some people do that as well. So I just want to warn you of that. But if you don't choose to make it so you shrink the array, you can still have the pop and DQ occur in constant time. It's just the issue primarily is the NQ and push operations. Those are the ones that are the issue here. So you can still do size, you can still do all of these, but the thing is, here the issue is NQ and push specifically. Like there's no way around it in more general terms. Is that clear, everybody? So you can still do size, you can still do is empty, you can still do all of these in constant time in the array-based approach. Just the issue is that when you do an NQ or push operation, you're going to have to resize the array if the array is full, which you don't have any guarantee that it's not going to happen, right? This is why I mentioned that practically speaking, you try to pick an appropriate length for the array. But I have some good news for you. Good news. So the bad news is that you're going to have it where you may have to do this array resizing, right? And the tip I will give you is that when you're resizing the array, you can, for example, make the array twice as long for your resizing. So when you expand the capacity of it, what you would do is you would do the process we talked about last day, but you would make sure that the length of the array, when you pick the length, it's twice as long, or any constant that is positive. So positive, I guess I should also mention that any positive that is greater than 1, that multiplicatively makes it longer, right? So for example, if I have it where it's 1.5 times longer than the original length. If you actually use this resizing scheme, what you should have is that over time, if you imagine that you're performing many of these insertions, what you should expect is that the behavior of, even though the worst case time complexity is big O of n, it actually still behaves like constant time in practice. So if you're wondering the justification of why I'm suggesting you might want to resize like this, as opposed to adding, say, 10 to the length of the array or 100 to the length of the array, instead I'm using more of like a geometric way of resizing. I talk more about this in CS210 if you're curious about this. This is closely related to a topic called amortized analysis. And what this amortized analysis does is it measures the worst case time per operation. And what you can show is that the worst case per operation is still big O of 1. So meaning that when you do many of these operations, you should expect it still to behave like constant time. It's just that when you resize it like this, it pushes that expensive operation of the array copies far enough away that if you have to do it, it only happens, but it happens infrequently. So if you're curious more about that, I'm always happy to chat about it, but I talk much more about this in 340. Are there any questions about the time complexities I have here? So I must stress for the array-based implementation, remember, size is empty. These take constant time. It's just the issue is just that when the array becomes full, you have to bite the bullet and take linear time. Is there any questions about that? Or is that pretty clear? This is one thing that's really nice about stacks and queues, is that their worst case time complexities are essentially optimal. It's not really much you could do more to speed them up. So one thing I do also want to mention is that when you're using an array-based approach, if the length of the array isn't too long, you might consider using that over the linked-based approach, because storing and creating nodes, it takes up space. And if these entries are right beside each other and the length of the array is not too big, you may consider that. Because we need the copy. Yeah. But yeah, no. Yeah, if there aren't any other questions, I want to make one other remark before we proceed to our new topic. I want to talk a little bit more about containers, just a little bit further, because you will be exposed to more kinds of containers, especially during the lab. I wanted to mention a couple other ones that... So I'll call this containers ahoy. Ahoy, mateys. So we've talked about a couple of containers. We talked about stacks and queues. Remember, the whole idea here is that I have a collection of elements that are all put together in this thing we call a container. When I have insertions and removals, they follow different rules. Like a stack follows our LIFO rules. A queue follows FIFO rules. But there could be other kinds of containers. So this isn't by any means the only two we'll talk about in this course. But I wanted to mention that there's more. There's more. For example, there's such a thing called a list, which I must stress that colloquially gets often thrown together with arrays very often when I talk about them because they're that elementary. So in fact, some languages, when you talk about an array, like they literally mean a list, but they're not really the same thing. It's just that a list is a type of container that I must stress that you'll talk about this one more in the lab. And you could think of it just like when you have say, a collection of elements, and you want to perform insertion, say at the front or at the back of the list, if you want to do an insertion somewhere in the list, you can maintain a couple different versions of these kinds of lists. For example, there's so-called unsorted lists, an unsorted list. There's also a sorted list. And it's very common for these types of list structures to be implemented using different linked-based structures or even just an array. So in fact, sometimes in discussions I'll just say, oh, you can use a list to represent it, but for simplicity, I'll just show you an array. That's a pretty common way of implementing a list, is just using an array, but you run into the same problem I talked about here, where if the array becomes full, you're going to have to make a larger array, right? But I must stress that there's other ways of implementing a list, but the whole idea here is that you can perform insertions on a list, somewhere in the list, or you can find a particular element in the list, or you can insert at the front or the back, or you may want to traverse through all the elements. These are very common operations that a list will have. You'll learn more about lists during the lab. In particular, you'll see the standard libraries version of a list. So one thing I also wanted to mention, that a common way of implementing a list is something called a doubly linked list. I'm not sure if you've ever heard of a doubly linked list before. Has anybody never heard of a doubly linked list? Don't be shy. I'm going to be showing you a picture anyways. And if you're familiar with a linked list, I assure you it's actually not that much different. In fact, there's at least a couple different ways you can have a doubly linked list. So this is commonly implemented using a doubly linked list. So I'm going to show you a picture of what one of these doubly linked lists looks like. So I must stress that there's a couple of useful ways to represent a doubly linked list, but I'll show you one of them. And the name sort of gives it away. So you know how when I have a node in our linked list, normally we have a node that's like this, right? Where I have a node, it has a data attribute, and I have a next attribute, right? Those are my two attributes I normally have in a node for a linked list, right? This is my data here, and if I want to connect my node to another node, I can point at it using the next attribute, right? And normally I would have a head of a linked list. Or if I wanted to modify the linked list, I can also include, just like my queue-based implementation, a tail, right? We called it rear, right? I pause for any butt jokes. I'm just joking. Anyways. So let me show you what the difference is between a regular node that you're familiar with versus a doubly linked lists node. And it's really simple. So this is what you're normally used to. Here's what a doubly linked lists node looks like. So you have the data. And as the name suggests, it says doubly linked. I'm just going to make myself a little bit more space here. You'd have some data. You would have a previous node and a next node. So there's a new attribute in the node called prev. And it's going to have, instead of it just being 2 parts, it's going to have 3 parts, exactly. So it's going to have the previous, my data, and the next attribute. So let me show you a picture of what I mean by this. So here's a picture. So, for example, a common configuration for a doubly linked list. So I'm just going to draw out some nodes here. And the cool part about this is that every algorithm you know about linked lists, for example, traversing a linked list, is just as applicable here. So just the thing is, now you have much more flexibility with it. So for example, here's 4 nodes. I'm going to have it so that I have a head for the linked list. And I'm going to have a tail, but I'll call it a tail just for the simplicity of discussion. Some people call it the trailer. In the context of a doubly linked list, but this will work for us. So the idea is this. So whenever I have a next attribute, I point it at the next node, but each one of my nodes will have a previous pointer, and it'll point back at the previous one. So if I have, say, each one of their data is just some pointer to some object, A, B, C, and D, like this, I'll have my next one, and it just points back at the previous one. So when you're implementing a doubly linked list, when you're traversing through the nodes, the big thing that you're going to notice that's a little different with the algorithms, as long as you want to maintain the previous pointers, is that you're going to have to make sure you update those as well. So for example, when you perform a deletion, you're going to have to make sure you update the previous pointer as well. But there's a big perk with the doubly linked list. So you'll notice that sometimes I must stress that it's common to have it where the first node's previous is null and the last node's next attribute is null, akin to just a regular old linked list. Sometimes people have it where there's actually a dummy node or a placeholder node that actually comes before and at the end of the doubly linked list that operate like a bit what amounts to a fake pointer so that you can point at something that's at the beginning and the end. Another common way is that you actually have it where the previous at the end here, sorry, at the leftmost side here, at the beginning of the linked list, you have it point back at head. So what happens is if you ever go back to prev, you come back to the exact same node over and over again. Sometimes people do it this way, but this is a very common representation for the doubly linked list. Same idea at the end. You can also change this so the next attribute is actually the tail, so it just points back at itself. So the check to see if you're at the end of the linked list is just really a check if you've seen yourself again, as opposed to null. But you'll find that this is pretty easy to adapt from the algorithms you're familiar with for a linked list. Just now the difference is that there's just one extra step, just making sure you update this previous pointer. But could anybody see a benefit of the doubly linked list as opposed to just a singly linked list? At least think of it from an implementation standpoint. Are there any ideas of what you might be able to achieve with this doubly linked list as opposed to just a singly linked list in a little bit less code? Well, yes, that's one thing. Somebody suggests it's easier to traverse. That's one thing most certainly. We can easily add and delete. That's the biggest one. That's the biggest one. Very good, very good. So you notice that if ever I want to go forwards in the linked list and backwards, I can do that in a doubly linked list. Likewise, this is the big perk with this, is that I don't have to hang around, I don't have to keep track of, say, the previous node. I have direct access to it. I don't have to like have another pointer that's delicately being handled. I know where it is and I'm keeping track of that information. So if you have a doubly linked list like this, it actually makes deletions and insertions even easier. Especially deletions, because a very common thing you have to do with a singly linked list, if I want to use that phrase, you would normally have it where you have two fingers, where what you do is you would have to keep track of the previous one that comes before it, and you would have to remove the appropriate node. This is actually something that you'll be doing on your next assignment, just with a singly linked list. So if you have never removed from a linked list before, you'll get to have some fun playing around with that. But the doubly linked list gives you a benefit that you actually have direct access to the previous one, so you don't actually have to, you don't need to keep track of another finger, you just have direct access to the previous node if it exists. So this makes it actually very easy to adapt for this list data structure. So if ever you need to traverse from front to back or back to front, specifically back to front, you will, for example, need to, you have actually the means to do this very easily. So note that I will not specifically test you on doubly linked lists, but you will find yourself running into them, especially if you start playing around with lists. But I think in the labs, I think you get exposed to the standard library, so the STL list. And typically lists are implemented using things like doubly linked lists, but you most certainly can implement it using an array, very similar to the ideas that we've actually seen. That's actually why I want you to see it more in the lab as opposed to here, is because you already know how to manipulate things in an array. You know how to manipulate things in a linked list, right? So I think there's not too much more I could add here without it repeating myself over and over again, right? It's just another container that follows another set of rules. But the thing is, the insertions and removals, we want to make them as easy as possible for us to implement. A doubly linked list is very effective for this. But yeah, no, one other one I wanted to mention. This one, we might get some time to play around with it on our last assignment, is something called a vector. You may have heard of these before. So another one is called a vector. You could think of this as a, well, in fact, it is a, you could think of this as a dynamically resizable array. In fact, it functions like this. So you know how I mentioned about how we have to resize our array in our array-based implementations? A vector actually provides this functionality. So it does, in fact, allocate more memory. So if you need more memory to store more things in your array, a vector is capable of doing this automatically for you. And it uses operations such as pushback, and it also has a popback. The names should remind you of some things we talked about with the stack, for example. They have names for these in the standard library, and you'll get some time to play around with them, especially, well, we might play around with it on the last assignment. But yeah, a vector is another kind of container. It's a dynamically resizable array or dynamic array. Some people call this a resizable array. But the big perk is that then you don't have to worry about resizing the array yourself. The vector will take care of it for you. So it's one really nice thing about vectors. And they have all sorts of operations that you're akin to from a list too. So I just wanted to mention a couple more of these containers because I assure you, you'll get some experience at some point to playing around with these. So for example, like lists, on the lab, vector, we might get to play around with them on the last assignment. So I thought I would mention these, but these are a couple more examples of containers. You'll find that, especially if you're very fond of C++, vectors are your best friend. They're really nice. So I encourage you, if you find yourself curious about them, go look into them. They're actually very interesting. But yeah, no, are there any questions about containers before we proceed? We're going to move on to a new topic. Are we excited about sorting? We're going to be talking more about sorting. Give me 2 thumbs up if you're looking forward to talking more about sorting. I'm getting some yeses here. Wonderful, wonderful. So we're going to be talking more about sorting. So in 115, I know that you've talked about sorting already. You've maybe talked about some of the more basic algorithms, which these are quite effective for smaller inputs. Like if you have a smaller or shorter length array, all the algorithms you've seen are quite effective for sorting. So what I want to do with you is show you some of the more workhorse-like sorting algorithms, ones that are very often used in practice. In particular, I'll be showing you one of them that's often considered like the top workhorse kind of sorting algorithm. There's other ones too out there. I must stress there's like hundreds of these kinds of algorithms out there. These are just some of the, I'm going to be showing you a couple of the classics. But I must assure you that there's even more out there that try to take the same kind of ideas I'm showing you here, and they take them even further. So my hope is just to expose you to some other ways of thinking about how we can sort objects. So that's my goal here. So I want to remind you that we're going to be considering the sorting problem. So we defined that earlier on in the course. But what I'm going to do is I'm going to be considering what we call comparable objects. So it means I'm going to be very general about how I'm going to be talking about these algorithms. So it means that if I want to talk about what a comparable object is to you, I have to define what that is. So you may have a really good grasp on this idea actually already, it's just that I'm just giving it a different name. For example, you're actually familiar with comparable objects. It's things like integers, numbers, strings, characters, they're all comparable objects. So what makes an object comparable is the fact that you can list them out from smallest to largest. So the main mechanism for this is what we often refer to as a compare to function. In C++, very commonly the function is just called compare. So for example, there's this thing, for example, for the standard library string, it's called compare, and it functions just like as I have right here. So if I give you 2 objects, x and y, of a given type, so we're going to compare, we want them so that they're comparable. What I would do is I would have a function called compare to, or compare, whichever is more appropriate. And it has this function. And I must stress that in C++, we have the ability to override operators. So what you do is, if you're doing this and you want to really just go bonkers with C++, you can override the operator to use this function. Say, for example, when you're doing comparisons. So the idea is that if you have a function called compare to, and I give you one object x, and I give you another object y is given as the input. If it spits out -1 or something like -1, it just means that x comes before y. So if you're thinking about this in terms of numbers, just imagine if x was a number, y was a number, and say they were both objects. If it gives you out -1, that means that x is a smaller number than y is. If it spits out 0, that means that x is the same as y. Their precedence doesn't really matter if I were to list them out from smallest to largest. So in this case, if I give you 5 and I give you another thing that's 5, say if they're both objects, like see these are actually like integer objects, and I look at their contents and I say, hey look, are they the same? And the answer would be that compare would spit out 0 for you. 1 just means that x comes after y. So for example, if I had 7 as x and 5 as y, that means that 7 should come after 5. So this is just to make things a little easier for us, but keep in mind that if you're talking about strings, we're talking about them being smaller or larger, usually lexicographically. But most certainly, if you ever want to come up with your own comparable type, just if you implement a function like this, called like compare to or compare, the functionality is very basic. As long as you're able to do this with any pair of objects of that type, you can call it comparable. But the big thing here is that we're going to see later on that there's actually a stricter way of talking about comparable objects. Here we're talking about, for those that are really into the mayonnaise or mustard, I'm just defining objects so that I can list them out in what we would call partial ordering. So that I can say, well, this one comes before this one, this object's the same as this object, or it comes after it. Is that clear, everybody? So for our discussions here, just for the sake of brevity, all my examples, I'm going to be using numbers, and I'm just going to assume that the numbers are distinct. They do not affect the algorithms, just to be very clear. The algorithms I'm going to give you all correctly operate no matter like what, as long as they're comparable objects. So some programming languages will actually have facilities to make sure that you can actually implement something called a comparable object. Some will have some things like an interface. Like we talked about the idea of interfaces. Some programming languages will actually have it where there's something called a comparable interface, and you can actually implement the comparable interface. Just like when we talked about with our ADTs, same idea. So the idea is that we can call it comparable if it has a compare to or compare function, whatever you want to call it. But does everybody understand the idea? I'm just going to presume that you can have comparable objects like this. And for simplicity, I'm just going to assume that we're going to be playing around with numbers. So is everybody okay with this so far? So I must stress that these sorting algorithms are rather general. You can actually tailor sorting to specific kinds of data types. But I'm not going to have enough time to focus on that this term. But if I had like an extra month, I would happily show you more. There's so many sorting algorithms out there, and some specifically tailored just, for example, just the integers. Okay. So if we're okay, let's start talking about some sorting algorithms. So I just want to remind you a little bit about sorting and different kinds of sorting algorithms. So we actually talked a little bit about this earlier on in the course, believe it or not. Remember, for example, we analyzed insertion sort, and we talked a little bit about some algorithms that we can use to solve the sorting problem, right? Can somebody tell me some of those? So can you tell me just a few different sorting algorithms that you're familiar with? So there's 3 in particular I know you know much more about. Like I know you've seen in some versions of them in 115. We talked about at least one of them here. So yes, so there's at least a couple. So I see insertion, I see selection. You may have heard of this other one. It starts with a B. And it's not binary. It's bubble sort. Yes. So I just want to make a couple remarks about basic sorting algorithms before we get a little ahead of ourselves. So I want to mention a couple of interesting concepts that sometimes will actually help you figure out which sorting algorithm might be appropriate for your, say if you're thinking about this from a utilitarian standpoint where you want to use it, and you're thinking, hey look, I want it because it has this one feature. I want to kind of touch upon a few of these kinds of things. So we've seen already some algorithms before, right? There's several others out there. I know some have also been mentioned in the chat too. I'm just going to touch on a few just here. So we've seen some sorting algorithms. Right? So for example, you may have seen bubble sort, selection sort. We talked specifically about insertion sort earlier. So the first thing I want to make a remark about is that all three of these have the same worst case time complexity. So that's the first thing I want to make a note for you about, is that all of them take big O of n squared. So all of these take big O of n squared time. And this is true both for worst and average. So it means if you ask me about the average case time complexity of any one of these three, I'll tell you it's big O of n squared. So their behavior is not really like, it's not going to deviate from quadratic on average. So you shouldn't expect it to be any worse. But most certainly it won't get much better than that. So just keep that in mind. One thing I want to mention, just for your sake, is that these are all effective for small data sets. So we already had this discussion near the beginning of the course. But what small means? I'm talking in this particular context, I'm talking about 10 or 20 elements, in contrast to some of the algorithms I'm going to show you here. So smaller numbers, say like 10, 20, 30, you'll actually find in some of the more standard library-esque libraries, like say for example like Java or in C++, when you break the problem down into a small enough piece, sometimes they actually switch what algorithm is being used to solve whatever that subarray or that part of the array is to be sorted. And oftentimes they pick up one of these three algorithms and do that. Very commonly insertion sort is used, but I've seen some other ones as well. So I just wanted to mention that these are effective. So if for smaller data sets, so if you find yourself just needing to sort like 10 elements or 20 elements or something like that, these are perfectly fine. Like they're fine. One perk I want to mention about all three of these algorithms is they're all examples of something called an in-place algorithm. So I must stress that there's two different notions. There's a notion of something called an in-place algorithm, and then there's sorting in place. These are two different things. I'm specifically talking about when somebody talks about an in-place algorithm. So what this means is that it uses a small constant amount of space So the idea is that I give you the input, and the idea is that your algorithm will transform the input and give you the output without needing any more than a constant amount of space. So very often the idea with the sorting algorithm is that I give you the input, it does the transformation of the input where it permutes around the elements, for example, and it doesn't actually use any more than a constant amount of space to temporarily store anything. For example, when you do a swap, you use a temporary variable, right? To temporarily store one of them so you can swap them properly, right? So this is something very common in all three of these algorithms when you perform a swap operation, right? So all three of these are in-place algorithms. So that's a feature that they have. So it means if you asked me about their extra space usage, all of these are big O of 1 for their space usage. At least when we talk about extra space, which I've always been talking about up to this point. So is that clear, everybody? So this is a feature that all three of these have. Some sorting algorithms do not have that feature. Some of them actually use additional space to temporarily store arrays, or they perform copies over entire arrays. So I'm trying to, right now, So what if the data gets bigger? Oh, that's a good question. So I must stress that, remember, we're just thinking about these three algorithms. Remember, the algorithms themselves, we're talking about, I give you an array of n elements, and its job is just to sort the array. All three of these can correctly do that. And I must stress that each one of them is actually just using a variant of the exact same idea. All it is that if there's an element out of order, I swap them to reduce the number of unordered or elements that are out of place, whether it be in context of one element against all of them, or say if I do it over each element. The idea is that I'm just trying to perform a swap to reduce the number of unsorted elements in total amongst if I were to add them up over each element. So each one is using this kind of idea in one way or the other, but the idea is that each one of these at some point actually checks that if the array is actually sorted, right? You'll notice that each one of them has some way of just scanning through the elements to see that it's actually sorted. So just to clarify, somebody's asking about what do you mean by small or big data set? Like, is there any number? No. It depends a lot on your application. But you'll find very often in sorting libraries, so if you find yourself looking, say if you ever find yourself go digging around in some of the source code for some of the standard library, or say if in something like Java, they also make their code public. If you ever go look around, they usually use these algorithms when, say, the data, say, is of length like 10 or 20 or 30. But I must stress, it always depends on what your goal is with these algorithms, because I'm thinking from more of a practical level when I think of small versus big. Because remember, at the end of the day, when we're comparing these algorithms, as far as we're concerned, they take quadratic time in the worst case, and also in the average case. So my goal here is I'm going to show you some other algorithms that are able to achieve either better worst case or better average case. And naturally, when you think about it, okay, so if these are really effective for smaller data sets, in contrast to these other ones, maybe there's a way I can use those more efficient algorithms for really big data sets, and then I can use them when they get really small, I can maybe use these ones. That's very often what actually happens in some of these standard libraries for optimization purposes. But most certainly, you can use the algorithms cold, clean turkey, kind of. You can just use them directly. I just want to mention that from a practical level, that often happens where when the problem is small enough, they just switch what algorithm you're using. Because you could do this if you're dealing with recursion, which is what we're going to be running into. But I wanted to give you just a quick example just to convince you that all three of these are correct. Because we don't have enough time to talk about each one and prove each one's correct. But they're all based on the same idea. It's just ultimately, I have two elements. I would like to make one of the elements a little less out of order. So what I do is I swap it to try to put it into the correct spot at that time. So if I look over all my elements, I'm trying to reduce the number of what we would call inversions, the number of times I would need to actually swap them to put them back in the correct order. Bubble sort does this by literally just doing it against all the pairs, right? That's what bubble sort does. So that's how bubble sort assures its correctness. Selection sort does something quite similar to this, but it's much more similar, almost in kind of a backwards way, to insertion sort. In insertion sort, the idea is that each time I incorporate another element, right, I imagine I have my array, and all I do is I successively build larger and larger partially sorted arrays. So if I have one element, you can agree with me, if I only look at one element, that in itself is partially sorted already. In fact, it is sorted if it's just one element, right? And what I do is I successively introduce each element and I move it over to the appropriate spot by swapping over and pushing them along. I shift it over. So the way the correctness works for insertion sort is that each time you incorporate another element, you put each element into the appropriate spot such that wherever I put my box, each time I grow up by one, you could say that every element in that subarray is partially sorted. And if you do this over all the elements, it has to be sorted. In fact, that's very much how you would prove this, is that each time you can guarantee that it's partially sorted up to those positions. So each time I introduce another position in, I shuffle over the appropriate elements. And that's actually how a lot of the proof goes down. You would use something like mathematical induction to guarantee this if you're proving it. But like I said, we're not going to focus so much that on in here. What I would like to do is talk about some sorting algorithms, like I said, that can achieve better worst case running times or better average case running times. So in fact, in many cases, they might be able to do pretty effectively. One thing I want to stress is that some of these algorithms are able to achieve, like these ones, these three here. The one big thing that they do is they do eventually just check if it's sorted or not, right? Like at some point there's going to be where it scans from left to right, whether it be through some process like this, or it does it as a literal check. It will do this. So if you give it something that's already sorted, for some of these, it'll just simply run in linear time in the best case. Others will not, but most certainly, I'm not going to focus so much on here. I want to talk more about what we can do in average case to improve this quadratic case, quadratic running time. But I must stress, you're going to see why I mean that some of these will be pretty handy for smaller data sets, especially ones that are already partially sorted. Ones that are very close to being sorted, these are pretty good. But I'm not going to get too quantitative about that, at least here. So the first algorithm I would like to talk about is quicksort. So this is very often regarded as like the workhorse sorting algorithm. This is one of the classics out there. It was developed in the mid-20th century. And it does something that's kind of like the reverse of what I've just described to you about how these all work, right? So in my algorithms for these, the idea is that I have an element. If it's out of place, I put it into the appropriate spot, like an insertion sort, right? Well, what I'm going to do is I'm going to flip this idea completely on its head. So suppose I have my friends here. I brought the crew over. I also picked up a Ninja Turtle here too. Cowabunga, everybody. So what I got here, I got some friends here, and imagine I want to sort them by their heights. So if I were to do something like insertion sort, I would start off here at the leftmost side, and each time I would incorporate another element, and I would perform the shuffle over. But notice each time I do it with respect to the given element I'm looking at. Well, what if I literally did this? What if I gave you a given element, and I try to sort everything around it, as opposed to looking at pairs and trying to swap, just thinking of them in terms of pairs. Think about it as I give you one element. What if I just like sorted everything with respect to that one element? So for example, suppose I have the dinosaur here. So suppose I have the dinosaur, and I would like to know which elements are smaller or shorter than the dinosaur. The dinosaur sort of cheats because it's got this pointy horn. And which friends are taller than the dinosaur. So what I could always do, rather than trying to find where the dinosaur should be in the array, I ask, okay, how many elements are shorter, or how many of my friends are shorter than my dinosaur, and how many are taller than my dinosaur? And we're going to see something very interesting that comes as a result of this. So if I go through my friends, for example, notice that the turtle is definitely taller than the dinosaur, right? So we know that that's taller. I'm pretty sure the car's shorter. So if you were to lay them out like this now, notice that all my friends that are shorter than the dinosaur are on my left, all my friends that are taller than the dinosaur are on my right. So here's something interesting. When I frame it like I'm just trying to sort everything with respect to a given element, you're going to see that this is what the dinosaur in this example is going to be what we're going to call our pivot. What we're going to see is that if I do this, notice that every friend I have over here is shorter than the dinosaur. Every friend I have here is taller than the dinosaur. Does everybody see that? So, imagine I look at the Ninja Turtle. Again, cowabunga, everybody. It's Thursday. So what I could do is I could ask the same exact question, right? So how many of my friends, say in this group, are taller than the Ninja Turtle? And how many are shorter than the Ninja Turtle? So for example, my lovely green friend is in fact taller than the Ninja Turtle. And in this case, I think technically speaking, let me just I think the Ninja Turtle's cheating because the Ninja Turtle's arms are up. We're just going to go with that the Ninja Turtle is taller, even though I think they're pretty on par. Just Ninja Turtle's arms are up like this. I'm giving it to the Ninja Turtle, okay, everybody? But notice now, if I look at this one group here, shorter, taller, and if you can actually look at each one of these groups and do the exact same thing, but notice I only have one more friend in each one. There's no other friends to compare. Do you see how this might be a very effective idea to design a sorting algorithm? Does everybody see that? So notice that I'm actually redefining how you can sort recursively. Rather than thinking about it in terms of pairs where I try to put them in the appropriate spot, instead I wrap the world around the idea. I look at one element and I'm going to now arrange them all with respect to that one element, and then I can put them into two buckets. Then I can ask, okay, can I sort this bucket? And can I sort that bucket? And this is actually the core idea of quicksort. So if you understand that so far, I'm going to draw a fun picture just to illustrate this idea. You're actually really close to getting the entire picture of quicksort. So notice now this process is actually entirely recursive until I get to some point where I have no more friends I have to rearrange over, right? If I only have one friend, there's no other friends I need to compare myself against. But notice here that when I go through this entire process, now I've sorted them all from smallest to largest, right? Or sorry, shortest to tallest. So the idea is that we're just trying to frame all of them around a given element. This element I'm going to refer to as the pivot. So the idea will be every time I try to attempt to sort, you're going to see I'm going to select something called a pivot. For our discussions, I'm going to presume that the pivot's always the last position in whichever subarray, which a subarray, just for those that have never heard of this term, is just a subset or part of the array from some index to another index. So for example, when I sorted this group, this is the subarray. If this is 0, 1, 2, 3, 4, I'm considering the subarray from positions 2 to 4. So you're going to see that I'm going to take advantage of this fact, that I can do this. So I'm going to draw you a fun picture to illustrate this idea. So we're going to arrange elements around an element called the pivot. So we get, in the algorithm, we have this thing we select as the pivot. It's always going to be by default as the last element, but if ever you need to change it so that you pick a different pivot, all you have to do for our algorithm is just switch it into the last position, and the algorithm will proceed the exact same way. So sometimes the selection of the pivot plays a big role in the performance of the algorithm, which I'll talk about either today or next class. So let me draw you a picture what I mean by what we were just doing over there. So imagine I have a pivot. So I want to imagine that I have this pivot. I want to have it so that I can put the pivot in the middle where all of the elements that are smaller than the pivot are on the left side, and all of the elements that are bigger than the pivot are on the right side. So I'm going to have this pivot here. So we're going to split around the pivot X. And what we want to do is I want to set this up so I can recursively sort subarrays. So imagine I have these two groups. So imagine I have my two groups, these boxes here. I would like to sort both of these recursively. So these are going to be all the elements that are less than or equal to X. And these are all going to be elements that are greater than X. So I'm going to refer to one of these groups as S, and then the other one, actually no, I won't call, let's call it L. Let's call it L. So I'll refer to this one as L, and I'll call this group of elements G. So what I would like to do is I would like to sort these two buckets here, these two sets of elements. So I want to sort this and I want to sort this. But the point is I'm doing it recursively. So I'm breaking this array into two chunks, but that's figurative for us. We're literally just going to be looking at a subarray. And the idea is that if I sort this and I sort that, what I can do is I can imagine I have all of my elements again. If I sort this, and I sort this, and I put this right in the middle. I put it all together, it should be sorted, right? Just like my example with my lovely friends over here. So the whole idea here is that we're going to need some way to make it so that I can select a pivot, and I want to have it so I can define this group L and this group G. Then I'm going to then proceed to sort these recursively. But what does that mean recursively? It's just we're going to apply quicksort to this one and quicksort to that one. And we're going to keep doing this until these subarrays are too small. So somebody's asking, how do you pick the pivot? So what I'm going to presume is that it's always going to be in the last spot in the subarray that we're considering. But I must stress, so this pivot, just for those that are going to be, you'll see this shortly. So we're going to presume is the last element. You have actually control of the selection of this pivot. In practice, sometimes picking one pivot choice consistently actually improves the performance, but might be a little bit more difficult to compute. Other times it actually is that picking a certain kind of pivot actually creates worst case instances that are ones that are easy to check for, but most certainly you wouldn't like to have. So I want to kind of put this all together. So I have my picture here. So this is what I would like to have happen. Is some way I would like to have it. So I have this X here. That's the pivot. So imagine it's over here on the furthest right. And I want to make it into these two groups so I can sort each one of these recursively. So each one of these is being done recursively. So this sorting and that sorting, they're both happening recursively. Until we have no more elements to sort in each one of the groups, either 1 or 0. So let me recap this all together, and then we will talk more about how this works. So I'm going to try to put this together with what we did earlier. So I must stress, I'm going to give you an overview of the way quicksort works. And I must stress, I'm going to give it more in a general form, and then I'll talk more specifically of a classic way of describing quicksort to you in pseudocode. So there's going to be kind of two big pieces for this process, but I just want to give you an overview of the idea first, because there's several different ways you can write quicksort out, depending on which data structures you would like to use. So for example, you can define quicksort using entirely lists, for example. We talked about lists earlier today. You can define it entirely in terms of operations you would apply on a list. In this case, I'm just going to be thinking about it as just an array. So I must stress that the process I just described to you, where what I'm doing is I take the problem instance and I break it into smaller pieces, and I keep doing this. I keep breaking the problem down into smaller and smaller pieces. And then what I have is, like our base case for our recursive algorithm, I take these smaller pieces that now I can solve directly, I combine them to get the solution. This is a common algorithm design technique called divide and conquer. So this is actually an example of divide and conquer. You'll learn a bit more about divide and conquer in 340, but this is one of these hallmark examples. The other algorithm I'm going to show you is also a divide and conquer algorithm. So we adopt an algorithm design technique called divide and conquer. Called divide and conquer. And if you know what that phrase means, it's pretty much the exact same idea I just described to you. You may have heard it in all sorts of different contexts. You can think of like military, it's like a strategy. So what does that mean? We divide the problem into subproblems. Recursively. So we're just going to break the problem down into smaller and smaller chunks. Recursively solve each. Then conquer the problem instance. By combining or putting together, all these sub-solutions. So a sub-solution, just to be clear, is a solution to a sub-problem. All these sub-solutions to solve the overall problem. So that's what the divide and conquer technique is. It's naturally describable using recursion. So many recursive algorithms use this divide and conquer strategy. So you may have actually seen this strategy. For example, we talk about binary search. Binary search uses an approach kind of like this. It's not necessarily as interesting, though. It doesn't really combine things from sub-solutions. It just sort of discards things, right? But the way conceptually it works is, yeah, you break the problem down into smaller and smaller chunks by discarding halves of the array, right? Until eventually you find it or you don't find it. So, just to give you a recap of what I said over here. So if the input, so I'm just going to call it S here, even though later I'm going to talk about it as an array. I just wanted to write it more generally as a higher level entity. So you can think of this as a list. You can think of this as an array, as long as you have direct access to elements in it. So it could be a vector. Has 0 or 1 element. It is sorted, right? If it has 0 or 1 element in S, it has to be sorted. You can think of S as a subarray. That's why I called it S. So if it has 1 element or no elements in it, it has to be sorted by definition, right? We talked about this earlier. So otherwise, there are 2 or more elements. Select the pivot. So we're going to select a pivot. So what I was referring to, what I called X over there, you're going to select this pivot. And this is going to be an element in S. Now place all elements in S except the pivot into 2 groups. 2 groups of elements. L and G, where L is going to be the elements less than or equal to the pivot X. So I'll just call it X for L. And elements greater than X for G. L and G, less than, greater than. It's very nice and easy if you think about it. So I break it into these 2 chunks. I have my pivot. The idea is that I then like I said over here, I'm just going to recursively sort. Recursively. Let's still say recursively. The microwave sort of melted that R over there. It's looking like, I don't know, it's kind of like cheese when you put it in a little too long. It just sort of starts lopping over. It says recursively sort both groups of elements L then G. Then lastly, just put them together, right? In order. Elements of L, then X, then G. So that's actually how quicksort is going to work at the highest level. So I thought I would just walk you through one quick example, and then we'll see how much time we have. So let's proceed over here. I just want to kind of walk you through this mentality that I had earlier, where I went through with my group of friends here. So the dividing aspect of this is this process where I identify L and G. So every time I recursively apply the sorting, every time I'm going to I select a pivot, then I have my L group and the G group. I'm going to keep doing this until I know that S is either going to have 0 or 1 element. And for each one of them that has 2 or more, I'm just going to keep subdividing like this. So the dividing part of the algorithm is where I take and I'm splitting it into those chunks, the L and G groups. And then the conquer part is where I take all of those cases, all the ones that are all sorted when they're really small. I've already arranged them nicely so that they're L, then X, then G. So the conquer comes from all of that work that happens when I break them all down, because I know how to solve each one of them. And you know how I talked about in practice how you can take something like a quicksort or something, and you can take that and adapt it with a different sorting algorithm? You can easily take my idea that I gave you over here. It's not really my idea, it's an idea we're talking about here. If the array is small enough, you can apply a different sorting algorithm to solve it directly. So I must stress that these recursive sorting algorithms are very easy to adapt to do things like this. So let me just show you what I mean. What? Get back here, camera. Get back here. Get back here. Get back here. So suppose I give you an array like this. Suppose I have 2, 3, 10, 10, 1, 5, 7, 11, and 4. So what I'm going to do is I'm going to pick 4 to be my pivot. You're going to find in the algorithm, I'm going to just presume that the last element in whatever I'm considering, in this case, if this is my whole array, but as you're going to see, I'm going to imagine it like I'm going to take it and put into buckets that are going to be in themselves sorted. So I'm always going to pick the last element in our algorithm, but as I said previously, if you ever need to have it where you pick a different element as the pivot, for our pseudocode that I'm going to give you either today or next class, what you do is you would swap whatever that element is with the last element, and you'd put it into this last spot, and you just continue with the way that we proceeded here. Okay? So same idea. Think of the dinosaur. So think of that dinosaur where I put all my friends on that are shorter than my dinosaur on the left side. Then I put all my friends that are taller than the dinosaur on the right side. So I'm going to make them into 2 groups so that if I were to sort the left group and the right groups, then I should be able to tell you how to sort, right? So look at this. I'm going to put all the elements that are less than or equal to 4 on this one in L, and this one I'm going to have all the ones that are greater than. So 2, 3, 1, and I think we also have, just 2, 3, and 1 here. Then I'm just going to, just for the sake of simplicity, I'm just going to kind of just scan through these. There's a more effective way of doing this that I'm going to show you. So we've got 10, 5, 7, and 11. So now I have L and G, and I say I'm going to recursively sort these two. So now I'm going to do the same exact thing. So notice that there are no elements less than or equal to 1 other than 1, but 1 we don't count, right? So 2 and 3 are all greater than the pivot. So I just place those into the G bucket. And then I would keep going down like this. See, watch this. See, then I have 3 as the pivot here. 2 is less than 3, so it goes in the left bucket, or less than bucket, and nothing goes into the right bucket, or a greater than bucket. Same idea over here. Actually, technically, all of these elements are less than 11, so I have 10, 5, and 7. Nothing in here. I pick 7 as the pivot here. And I must stress, the selection of the pivot doesn't change the correctness of this algorithm as long as it's a part of this bucket here. This group of elements. As long as it's the case, like I could have easily picked 10 to be the pivot instead, and this algorithm will still work. The whole idea is that I make it so that everything that is less than or equal to the pivot on the left side, then I have my pivot, then everything that's greater than the pivot goes on the right side. If no matter which pivot I select, like whatever thing I decide is the pivot, this will still allow me to rearrange them in the correct order, right? So notice 5 is in fact less than 7, and we have 10 here. But now notice that these are of size 1. This has nothing, that has size 1. Notice that what I've done here is I've gone through this divided process I talked about. So this is the divide phase of this algorithm. So it's breaking the problem into smaller and smaller pieces until eventually I have problems that I can easily solve. Then what I'm going to do is I'm going to do now this conquer phase. So now I'm going to pull this up, and I'm going to take all these sub-solutions and combine them to end up sorting the entire thing. So let's do the conquer part. I'm going to work my way up. So we're going to do the conquer phase now. I'm going to work my way back up. So the recursion is going to do all the work from here now. So I have 2. Then I have the pivot, then whatever's greater than. This one doesn't change, right? Okay, nothing in here. I have the pivot, then I have the greater stuff. So all of this, since that's already sorted, I'll put 1, 2, 3, like this. I'll just for the sake of clarity, I'll just leave whatever the pivot is, just so you know what it is. 5 is less than the pivot, so I have 5. 7 and 10, because 10 is greater than 7. I could do the same thing here. So I have 5, 7, and 10. And since there's nothing over here, I'm just going to leave that right there. And then, now I have everything that is less than or equal to the pivot. I know what the pivot is, and I know what's greater than the pivot. So let's just rewrite this right up here. Put the pivot right here, then put this right after the pivot, okay? Just like our boxes we had earlier. So I have 1, 2, 3, pivot, 5, 7, 10, 11. And now notice that my input array is now sorted. Does everybody see that? So all I've done is I've taken this idea of building everything around this pivot and now I've defined recursively how I can sort the array. So when we come back next time, we'll actually go through the pseudocode and we'll talk about this process. So how exactly do I put them into these 2 buckets, which I'll refer to as the partition subroutine or the partition method. So I'll be talking about that next day. So the reason why I mention this is because it's relevant for the assignment. So if you're looking at the 3rd problem on the assignment, don't worry. We'll talk about it on Tuesday, okay? So when we come back, we'll finish talking about quicksort, and we'll see how much time we have for merge sort, okay? So I want to say thank you very much, and have yourself a beautiful day. I'll see you later.